we will be looking at the problem statement for finding the number of connected components in an undirected graph. We will be building a solution in JavaScript using a depth-first search traversal approach. Before jumping into the solution, let's first try to understand the problem statement. We will be receiving an input of edges that will be looking something like this. So we will have 0, 1, 1, 2, 3, 4, let's say. How that looks charted into a graph is something like this. So we will have 0. We said 0 goes to 1. So 0 is going to 1, which basically means 1 is also going to 0 because this is an undirected graph. Then 1 goes to 2. So we will have 1 going to 2. Then we have 3, which is going to 4, which basically also means that 4 is going to 3. Now, after we have charted it into a graph, what can we see here? We have one connected component. What does a connected component mean? It means that you start from any node. From that, you can visit all the nodes that are there in that connected component. So if I start from 1, I can go to 0, I can go to 2. All the nodes are visible. I start from 3, I go to 4, I start from 4, I come back to 3. And these are two isolated components that are connected within themselves. That's why the output of this will be 2. And the aim here is to find this number of connected components within the graph that we are given based on the edges that we receive. And the number of vertices is also going to be passed to us. So in this case, we had 0, 1, 2, 3, 4. That would mean we have a total of 5 vertices. So we have 5 vertices in this case that were passed to us, and we were passed this edges input as well. Now that we have understood the problem statement a bit more, let's jump into the solution aspect. How can we determine that a component is connected or not? I will start from a not visited node. Let's say I start from 0. I will go from 0, the connected component is 1. Then from 1, I will go to its connected component, which is going to be 2 here. Then from 2, I see what is my not visited connected component. When I reach here, I just have 2 because 1 has already been visited. And when that happens, I have nowhere else to go, and the depth-first search traversal mechanism will just stop. I will keep going as deep as possible, and then whatever unvisited nodes I have, I will try to visit them. And similarly, now how do we go to the next one? Because we have found one connected component. Then from this, how do I go to the next one? So I will see all of my vertices that are not visited. If the vertex has not been visited, that will mean that it is a possibility that that can also form a connected component. So I visited my 0, I visited 1, I visited 2, then I am just left with 3 and 4. So I will start in a sequence. I will go to 3, which is unvisited. Then I will say, okay, from 3 go to all of it's connected, go to 4. From 4 I really cannot go anywhere else because it just goes back to 3, which is already visited. So I visit this and I visit this, and that's my second connected component. So as soon as I find a not visited component within this tracker, so I will start a depth-first search trigger. I will go in that specific depth-first search traversal sequence. I will keep visiting all the nodes that I see. I will mark them as visited, and then when this depth-first search traversal ends, I will basically go to my next vertex iteration and see if that vertex is visited. If that vertex is visited, that means I have already seen it as part of my depth-first search traversal. If not, I will increment my counter that I will keep track of to make sure that I keep track of this connected components. How that will look is something like this. So I will go from 0 to 1. Now, how do I know that I am going to go from 0 to 1? What is it that is telling me that there is a edge? This input that I have received is telling me that there is a edge. And to do this depth-first traversal, I will be building a adjacency list. The first step is that I have a adjacency list with me, and this adjacency list I will then traverse in a depth-first search fashion. What is this going to compose of? I will have all the vertices that I have received. So I have received 0, I have received 1, 2, 3 and 4. Then for 0, I will see what are its connected edges. I see this input as 0, 1, which would mean that there is a edge going from 0 to 1 and vice versa, because it's a undirected graph. And similarly from 1, I see there is an edge going to 0. Then I see from 1 there is an edge going to 2 also. So it is not just 0, there is also going to be 2 here. And similarly for 2, 1 is going to be an edge because it's reversed. Then I see 3, 4. So from 3 I see a edge going to 4, and from 4 I see a edge going to 3. So this is going to be my adjacency list matrix that I built. That is the graphical representation of the nodes that we have. And then we traverse each vertex that we find in a depth first search traversal. So I will start from 0. I will see 0, I will mark it as visited. So once I mark this as visited, then I go to my next vertex that I can go to, which is 1 here. I will go to 1. For 1, then I will see what is the components that need to be visited. I see 0 here, I see 2. 0 has already been marked as visited, so I don't need to visit it again, because then we'll just be redoing the same thing additionally, which is not required. And then from 1, I will go to 2. Then from 2, I will see what its connected edges going to which vertexes. So this vertex is just 1. 2 is going back to 1, but 1 is already visited. So I don't go anywhere from there. I just mark 2 as visited also. Now I have completed one sequence of my DFS. After this sequence, what next? I am still going through my vertices that I have. So I went through my first vertex. I found this root traversal mechanism wherein I went from 0 to 1 to 2. And in the first sequence itself, I visited 1 and 2 as well. So when I go to 2 and 3, I know that they are already visited. So I skip them. Then I go to my 3. 3, I will see is not visited. In that case, I will have to increment my counter. So in the first sequence, I incremented my counter to 1 because 0 was unvisited. Then I encountered immediately after that 1 and 2 in the same sequence, after which I went to 3, which was unvisited. So I increment my counter to 2, and with 3 going to 4. And then I see 4 where it goes back to 3. 3 is already visited, so I just mark it as visited, and this is my second DFS sequence. So I have found 2 DFS sequences, and these are my connected components that I am supposed to be returning. And that's pretty much in terms of the logic that we are going to be following here. Let's convert whatever we covered so far into code. First, adjacency list will be the graphical representation of the vertices that we have received. And after we have computed the value of connected components, we just want to return it. So I will just keep a counter here that gives me a track of how many connected components are there in this graph that we are going to be building. And I'm just going to return the counter value at the end as to how many components are present. And then to build this adjacency list, what I will do is just say let adjacency list be a new map, because it's going to store against each vertex what is its list that it is having edges to. Now we want to build an adjacency list. To do that, we first have to initialize all the vertices against the adjacency array that we are going to keep track of. And to do that, I will just say for let I is equal to 0, I will go up to n, I will just do I++, and here I will initialize the list. That will just look something like adjacency list dot set. I have my index that is currently running, which is I, and I will put an empty array against it. So this is the initialization part. Now I will fill this adjacency list with the connections that I have received from my edges array. I will start from I. I will go from 0 up to the length of the edges that I have with me, and I will just say I++. Now I want to fill within the adjacency list that I have. What is the value I want to fill against? So when I receive 0, 1, I want to fill against 0, 1. What is the value that represents 0 here? So I will say against 0, which is basically going to be edges of I, and the 0th value against that, because it's an array, I will just directly get a reference when I do a get. So within the list of this adjacency, there is a map I will get the value from the map, I get the reference, and within the reference itself, I push the corresponding value. I push I comma 1. So this value at this index is going to be 1, which is going to get pushed. Now we said this is going to be a undirected graph, and because it's an undirected graph, the mapping is going to be two-way. What I mean by that is when 0 is connected to 1, 1 is also connected to 0, and I will just say also 1 being connected to 0 in this case. And this will give us the adjacency list here that we are looking at once all the iterations are completed. After we have built our adjacency list, it's time to do a depth first search traversal. And I will just go from 0 up till the number of vertices that I have, which is basically n. I will keep going forward, and I want to do a DFS. But I want to do a DFS only if the vertex has not been visited. And how do I keep track of it is also going to be via a map that is going to be, let's say, a scene map. And I will only say that if I have not seen the map. So if scene doesn't have this specific index that I'm looking for, that means that I have identified a potential candidate for a new component, and I will just increment my counter. After I increment my counter, I will just do a depth first search traversal with my component that is the new candidate, which is going to be this vertex I, and I will just pass I as part of my call to DFS. Now let's build this DFS. So how is DFS going to look? Is something like this. I will just take a current vertex that is going to be running through, and as soon as I visit the vertex, I will mark it within my scene array as scene.set this one as true. So I have visited my current vertex. After I visit my current vertex, what is the next step? I went to 1, let's say. So from 1, I have the possibility of going to 0 and 2. Now 0 has already been visited, so I have to make sure that it has not been visited, then only visited, and I go through all the elements that are dependent against 1. So from 1, where are the edges going to, which is 0, 2. And how do I get this? I get that from the adjacency list. So for let next of, from the adjacency list I have, for this specific vertex, I get all the adjacent vertices, and then I navigate these vertices if I have not seen those vertices. So only if I have not seen the vertices, then I do a depth first search traversal to this vertex that I have encountered. And that's pretty much it in terms of implementation that we have here. The first step is just building the adjacency list. After we have the adjacency list with us, we do a depth first search traversal, and every time we found a vertex that has not been visited in the current DFS sequence, which will mean it's a separate connected component. And I just run through this loop, and at the end I am left with the counter which I'm going to return. And that's it. The time complexity involved here is going to be divided into two parts. The first part we said is building the adjacency list. Now, how much time is it going to build this adjacency list? The time taken will depend on the number of edges we have received. The time complexity involved to build the adjacency list is going to be dependent on the number of edges we have received here. And the number of edges, let's say the time complexity representing them is going to be big O of E, where E is the number of edges that we have received. Now that we have found the time complexity of building the adjacency list, the next part is doing a depth first search traversal. And how long can this depth first search traversal take? Depends on the number of vertices that we have. And the number of vertices that we have, let's say it's going to be time complexity of big O of V. And that's why the total time complexity, which is split into these two components, is going to be big O of E plus big O of V. And I will just say the overall time complexity that is going to be involved here is going to be big O of V plus E, where V is the number of vertices we have and E is the number of edges we have. Similarly, the overall space complexity will also be big O of V plus E. Reason being that the DFS is going to occupy space for the number of vertices that we have in the call stack. As we keep on making a call and going deep down in the recursive fashion, that call stack is going to occupy space. Number of vertices which we have, which are going to make this DFS calls. So that the part component comes with big O of V here, and then we have this adjacency list that is going to store the edges within its map, and that space itself is going to be dependent on the number of edges that we have here. That's why the E component. So overall space complexity becomes big O of V plus big O of E, which is big O of V plus E. And that's pretty much it in terms of implementation. Thank you for watching. Please like and subscribe.